Hi guys, today we're going to be solving Impersonator2 Ethernaut challenge. This is a very interesting challenge that once again deals with digital signatures and the various vulnerabilities that can come with them. So let's take a look. The goal of this level is for you to steal the funds from the contract. Things that may help to look carefully at the two signatures that the owner used. Now, looking quickly at the contract, we see that we have the setAdmin function and the switchlock function that both use signatures. In this case, we also use a new admin. We basically verify, well, we first get a hashed message. We verify this hashed message and signature. We increment the nonce, and we set the new admin. And similarly here, we get a hashed message. We verify it with the signature. We increment the nonce, and we change the locked value. And that's pretty much it. So let's grab our instance address. And let's take a look at the transactions on the Etherscan. So if we paste the transaction and if we go into internal transactions, here, here, and here, so we see that we have a switch lock, and here is the signature, and then we have the set admin, and here's the signature, and it's not hard to see that the R value is exactly the same for both signatures. Now, why is this a problem? Well, we can refer to our favorite Wikipedia article on elliptic curve cryptography and the signature algorithms. So you remember we looked at this article in detail when we were solving the challenge, basically the previous challenge, elliptic token. So you can check out my video on this challenge. But basically, here in this particular paragraph, we see that it is not only required for K to be secret, but it is also crucial to select a different K for different signatures. And if we remember, K is actually this random integer here, which gets translated into an R. So we have the same R, it means that we use the same K. And if we use the same K, it means that we can solve for DA, the private key. And basically, we will first derive a K value of K using this equation, and then we derive the private key using this equation. So that's going to be our strategy, and let's now open Remix, and I will basically copy all of our code into it. So here we go. We've already done this several times. I will create a contract called Impersonator2, and I'll adjust the compiler to be 28. And let's just get some, as usual, adjust the links so that our contract compiles. So this should do it. And we also need to initialize an ownable to message.sender. And we also have a small problem here is that ECDSA, the most recent version, does not have this method. And we actually need to include message hash utils. So let me just include this extra import. And once again, it's called this. So we will import message hash utils from this link. And down here, we will simply replace ECDSA by message hash utils, and our contract should compile. So let's compile it. And let's once again grab the instance address. And let's go to browser extension Sepolia and check out this contract very, very quickly. So we see that the nonce is 2. This is the owner. So let's grab the owner. And we also will have the admin. So we might need these two addresses. And let us also open a terminal right away. And I will make a directory called Impersonator2. Why not? And I will just open a VS Code window and a new terminal, and I will just initialize a new node project, and I will add VM, and I will add in index.js. And basically, we need to look at what we need here. So we need to reproduce these formulas. So we need our various elements of the signature. So let's do R. So we have an R, we have an S, and we have a Z, excuse me, Z. And we also, for the second signature, the R is the same, but we will have an S prime, and we'll have a Z prime. And we will use big int notations. So the R, we can get that directly from Etherscan. So this is the value of R. We just put 0x. There we go. Now similarly for S, we have it right here. Big int 0x. And yes, now we will have an S prime. Big int 0x. There we go. Now we will need to compute Z's, and Z's are simply going to be the message hashes. So for that, I'm going to have a little attack contract. And I'm going to get a function which basically will get me the Z. And it's going to be external, and it's going to be pure. And it's going to return a uint 256. And here, I will just return something. So now the first Z we need is for the first signature, and this would be the switch lock. So the switch lock function is going to be here. And really, the Z we're looking for is the hash message of message. So we would like to have this hash message function, first of all, in our attack contract. And then for the switch lock, we will have basically the hash message of the message. So we will return this, but then what is the message? Well, the message is simply this. So string memory message from in switch lock is going to be, this encode packed value. So let's just go ahead and replace message with this. And our nonce, so we know that our nonce is 2 right now, but when we called this function initially, this nonce was 0. So we're just going to write uint 256 of 0. And we also need to be using strings for uint 256. And there we go. So we're going to compile this, and we're going to switch to a regular remix instance, and we're going to get this, and this is our basically the value of our Z as a big integer. So we're going to go ahead and paste it here, and we're going to do something very similar to Z prime, except Z prime is going to be for the set admin, and the message is going to be this particular value. So let me just copy this. So the hash message, let me just get this correctly. There we go. So the new admin was this admin value that we had read before. And the nonce this time will be uint 256 of 1, because after the initial call, As we remember, after switch lock, the nonce gets incremented. So now we are at 1. So I will compile this. I will remove this contract, and I will deploy the attack contract again. And I will get our z value, and this is our value, which I can paste here. So here we go. We have almost everything. We also going to need our n, the big modulo constant that we use for all of our calculations. And I'm just going to open the ECDSA contract and simply copy paste it. So there we go. And it's going to be big int of this. Okay, so now we are really ready to do our calculations. So let's see what is our formula. So k is z minus z prime divided by s minus s prime. So z minus z prime divided by s minus s prime. Now, of course, this division is really the inverse, modulo n. And I'm just going to copy paste here the extended Euclidean algorithm. So there we go, except here we're not going to be using TypeScript, so we're just going to remove these big ints. So yeah, so this is our find inverse function. Again, you can check out our video for the derivation of this algorithm and why this gives the extended Euclidean algorithm. And basically here, instead of dividing, we're going to be multiplying by find inverse. And here, of course, we need to include the n. And we always would like to keep things relatively small, so we'll just do modulo n after every multiplication, just to be sure that there's no mistake. And then the next thing will be basically to compute this d. D is going to be sk minus z divided by r. So s times k minus z divided by r, but that's of course just multiplied by find inverse of r and n. And we can also insert some modulo n's here just to be sure that we're always smaller than n. And we're going to call this d. So this is going to be our private key. So let's just make console log everything to make sure that things are working so far. So yeah, there we go. I'm assuming it does appear to be working. So let's just, so I think it's called from private or private key to account. Private key to account. So we need 2 hexadecimal. We need our D, and we need size to be 32. So we're going to have an account, and then we're going to have, let's just console log count.address. So let's see if this is working. So there appears to be some error. Yeah, so of course, the error here comes from the fact that I forgot to modulo, and we have basically our numbers are a little too big. So now that I've corrected this, this is the address that we got, and if we go back and compare it to our owner address, so I do believe that we have, yeah, we have exactly the same address. So we see that we have derived the private key of the owner, and the owner's address has become completely compromised because the owner use the same key for two different signatures. So that's great. We know that we are on the right path. So now we simply need to sign certain messages. So let me just do an async function here. Get signature, and we'll do const signature is equal to await account dot sign, and we're going to have some hash here. And we're going to console.log the signature, and we're going to call this function here, and we don't need this anymore. And basically we need to figure out what we need to do here, and let's actually change it into a let, and let's do this again because we're going to be needing two signatures. The reason is basically here in the contract, our contract is presently locked because when this switch lock has been called one time, as we saw on Etherscan, our contract became locked. So we need to unlock it by calling this function first, and then we need to call setAdmin, and then only then we can actually withdraw. So we need to call twice, and for each one we will need a signature. This is why we're going to need two signatures. And so the first signature is going to be the unlock signature. So again, this is going to be the message that we need. So let's just go back and over here. So this is the message, and now the nonce is going to be UN256 of 2. So now this is the current nonce that we're going to need. And also I don't really want to an integer anymore. I would like to have it as a bytes 32. So let's just remove this. So let's just compile this and deploy the attack contract. And yeah, so this is going to be our first hash to unlock the contract. And we're just going to paste it here. Now our second hash is going to be to set ourselves as admin. So again, we need this message now. So we're going to paste it right here. So the new admin is going to have to be the player. So this is our player address. And our nonce is going to be uint256 of 3, as it will be incremented. So let's compile this, deploy, and we get our hash, and we're going to put it here. So there we go. Let's just clear this and run this, and here we have our two signatures. So now we are ready to switch back to our instance and Sepolia. So let's just go to browser extension, Sepolia, and we need the Impersonator2 at this address. And so let us try to, first of all, switch the lock. So we're going to need this first signature. And there we go. So the transaction seems to pass. So that means that now our contract is unlocked. And the next thing will be to set ourselves as admin. So yeah, there we go. So to set ourselves as admin, we need the signature. And now we would like to have the player address as the new admin. So let's just transact, confirm. Again, if something was wrong, we would probably get some kind of warning. But here it seems that everything is passing. So we're just going to give it a few seconds. And then we're going to be able to basically check the admin of the contract. And I'm actually not sure if it came through. Yeah, so we see that it actually already came through. So we are the admin of the contract. So in principle, now we can simply withdraw the funds and we have passed the challenge. So I hope this this vulnerability shows you how important it is to actually, whenever you're using digital signatures in the real world, you have to be very well advised and you have to take care not to reuse the same value of R. And I think there is an example where they say that basically Sony did not properly implement the algorithm because K was static instead of random. But this was back in 2010. But of course, this vulnerability is still very, very relevant today. So just to be sure, let's submit the instance and make sure that we have passed this challenge. And just give it a few seconds. There we go. So I hope you learned something today. Thank you very much for watching, and I will see you next time.